Sorry about getting cut off there. We can only do 15 minutes per video, so I wasn't watching the time. So we're going to start here. We're continuing 11.2. Okay, we're continuing 11.2. Now, we've talked before about if we have a product, right? A product under a root, I can break that up into the product of the two roots, right? And when we did this, notice their example. Whenever you break them up, you're trying to find, in this case, a perfect cube. When we did something that looked like this, square root, we were trying to find a perfect square under there, right? Because that could be simplified to 2. They're doing it here, finding a cube. That's a perfect cube right there, right? So you have to watch what root you're working with. All right, then we talked about if you had a fraction under a radical, you can make it a fraction of 2 radicals, right? It might be easier to figure out the answer that way. Who wants to take the square root of this, right? That's some crazy number. But if we break it up into 2 radicals, we easily get the answer. So let's try some, okay? It's a simplify the expression using the properties of nth roots. Assume that all the variables are positive. We're not going to worry about that. We didn't even talk about it. And rationalize any irrational denominators. If we hit that, we'll show you what that means. We've rationalized denominators in the past. So, let's see. We want to try to do a cube root. Well, sometimes when we have big numbers like this, we got to figure out a power for those to try to be able to simplify. So what we can do is we can take this 256 and see what are its factors, right? Well, it turns, I could do a factor tree, couldn't I? Right? I could do 2, and what would this be? 128. Starting to look interesting here, guys. What did I, in the last video, I said, oh, 2 to the 6th was 64, wasn't it? Well, that means 2 to the 7th, 2 to the 8th. 256 is 2 to the 8th, isn't it? So I'm going to rewrite this. 2 to the 8th, x to the 3rd, y to the 7th. All right. Now I'm looking for perfect cubes, right? Well, 2 to the 3rd is a perfect cube, right? Notice I have 2 of these under here. So if I pulled out what was a perfect cube, I have a 2 to the 3rd. I have a 2 to the 3rd. And the part that's not perfect are the 2 squared that's left. Now, if I look at my x's, I have a perfect cube right there. If I look at my y's, I have a y to the 3rd and a y to the 3rd. And then I have this y left over. So I can rewrite this. I'm pulling all the perfect cubes because I'm looking for cube roots. I'm separating them out because it's helping me see how to simplify. So, all right, the cube root of 2 to the 3rd is 2. The cube root of 2 to the 3rd is 2. The cube root of x to the 3rd is x. The cube root of y to the 3rd is y. The cube root of y to the 3rd is y. And this cannot be simplified, right? So my final answer is going to be 2 times 2 is 4. 4xy squared times the cube root of 2 squared y. Right? I could write this as 2 squared, or I could write it as 4. So what we're trying to do is pull out all the perfect, in this case it was perfect cubes. In this case it's perfect 4th powers, or, to the 4th power. So let's see how this one plays out. So I have a ratio. I'm going to do this. 4th root of 81, over the 4th root of x. Well, gang, the 4th root of 81, again, once you play around with it, you'll see it. 3 times 3 is 9 times 3 is 27 times 3 is 81. 4th root of 81 is simply 3. Then the 4th root of x. Well, when we're rationalizing, we're trying to get the denominator to be a perfect whatever, when you and I did something like this, notice we had a square root. So what we needed to do was multiply like this, because then underneath here I have 2 times 2. I have a perfect square under there, don't I? And that turned into square root of 2 over 4. Those are the same value with a rationalized denominator. So when I have a 4th power, I need a perfect 4th, something to the 4th underneath there. Well, I only have something to the 1st power. So I'm going to have to multiply by the 4th power of x to the 3rd over the 4th power of x to the 3rd. That just equals 1, right? Just equals 1. We're not changing the value, we're only changing the form. So this becomes 3 times the 4th root of x to the 3rd over the 4th root of x to the 4th, right? That no longer will be in a radical. 3 times the 4th root of x to the 3rd over x. That is your answer. Okay? So you're always, when you're rationalizing denominators, you got to get a perfect. If it's a square root, you need a perfect cube under there. If it's a cube root, you need a perfect, If it's a square root, you need a perfect square, right? If it's a cube root, you need a perfect cube. If it's a 4th root, you need a perfect something to the 4th power. That's how we rationalize denominators, okay? All right, so we're going to try a word problem. And it says, rewriting a radical function model. Okay, so when you find or apply a function model involving rationals or radicals, you can use the properties in this lesson to simplify. So it says, a can that is twice as tall as its radius has this minimum surface area right here. Now, use the property of rational exponents to simplify this expression. Notice that I have a constant and a pi inside the 2/3, but I also have them outside. So we're going to try to simplify this model, okay? And then it says graph the model. Well, we're not necessarily worried about that, but let's see. Whoops. Okay. Shoot, there's really no room to write. That's okay. So if I take this model, and I'm going to rewrite it here. Come over here. Equals 6 pi. And then I'm applying this 2/3 to everything in here. V to the 2/3, 2 to the 2/3, pi to the 2/3. Right? I'm applying it to everything. Now, let's see. Notice that I have 6 pi here. I can write 6 as 3 times 2, can I? And then I have a pi. I'm going to back up. It might be easier if I just do this like this. Right? So now my equation, I changed my 6 a little. So notice this is now 2 pi to the 1st power. And I have v to the 2/3. And I have 2 pi to the 2/3. Now notice I can work with that. All right, so I have 3. And then this is 2 pi to the 1 minus 2/3, isn't it? 2 pi to the 1 minus 2/3. Yep, and then I have a v to the 2/3. So I'm going to bring it over here for a second. Now, if I were trying to find this number, here it says with the coefficient, right? Coefficients are the constants or numbers in front of the variable. So 2 pi to the 1/3 is my coefficient, isn't it? So if I simply plug that in my calculator, I get approximately 5.54 v to the 2/3. Right, so this was simplifying an expression using what we learned about rational exponents or radicals, right? So we're at the end of this 11.2 video. I'm going to post a homework sheet on PowerSchool as well, Okay, so watch these videos, see what you think, try the homework. All right, thank you.